So I want you to consider the following question. What happens when you put the ends of two magnets near each other? When you're dealing with magnets, we know that there are two different poles to the magnet. If you put the same pole towards one another, they repel. If you take the opposites, they attract. So how might that relate to a polar molecule? Like a magnet, we know that polar molecules have a polar or a positive end and a negative end. Thinking about the concept of opposites attract, we come up with the two terminologies. We have intramolecular attraction within the particle, such as covalent bonds. And we have intermolecular attraction, which means between particles. So when we're talking about polarity, you can see that polar molecules actually have an attraction for one another, just like a magnet. Opposite ends, they attract. Same end, they repel. Looking at the following diagram, you can see that the oxygen, which is the slightly negative end, is attracted to the hydrogens, the slightly positive. The reason that we talk about intermolecular forces is that intermolecular forces actually can affect properties such as your boiling point, melting point, viscosity, and cohesion of your actual substance. When we're taking into consideration water, we know that water has a high intermolecular forces, a relatively high boiling point for something that's covalently bonded, can absorb and release large amounts of energy, has a very high surface tension, which we'll talk about later on, solubility, able to dissolve things, which we've looked at in previous lessons, and the density of ice is actually less than that of a liquid. So when we're looking at these, we're going to take into comparison hydrogen and fluorine, chlorine and bromine, oxygen bonded with oxygen. Looking at the difference in electronegativity, you can see the larger the difference, which we talked about earlier, the more polar something is. The more polar something is, the stronger the intermolecular forces. If you are slightly polar with a lower difference in electronegativity, you're going to be medium strength in your intermolecular forces. And if you have no difference at all, well then you're nonpolar and you have a very, very, very weak intermolecular forces. So when we look at just water, okay, we know that there's a big difference in electronegativity. That big difference in electronegativity results in very strong IMFs, or intermolecular forces. As a result, we know that there's a high melting point, a higher boiling point. There's cohesion within the water, adhesion, so ability to join together or join with something else, a high surface tension, high viscosity, and a very low vapor pressure. When we're looking at water, there's actually a particular type of intermolecular forces that is going on. This is the strongest version of hydrogen bonding, or of intermolecular forces, which is called hydrogen bonding. Hydrogen bonding is the attraction between polar molecules. H and X bond, creating a very, very polar bond, thus a very strong attraction for other molecules within the substance. The bigger the difference in electronegativity, the stronger the attraction. Hydrogen bonding is formed when hydrogen bonds with either nitrogen, oxygen, or fluorine. As you can see here, we have hydrogen bonds that are present between the hydrogen and the nitrogen. Since these two are very opposite or very different in electronegativity, we have a very high difference in slightly negative and slightly positive, thus causing the molecules to join together. Another form of intermolecular forces that we have is what's called a dipole-dipole. Dipole-dipole is an attraction between polar molecules. So intermolecular forces, when we have a dipole-dipole, the attraction between the polar molecules is just the positive ends are attracted to the negative ends, and the negative ends are attracted to the positive ends, and what causes all of these molecules to join together. Opposite charges attract just like our magnets. Like charges repel, same as with our magnets. The last type of intermolecular force that we have which is the weakest force, is what's called dispersion, or van der Waals forces of attraction. What they are is they're a temporary distortion of electron cloud. What this does is it causes a temporary polar molecule. A second atom can be induced or influenced to become polar, thus weakly attracting the first atom. So if you're looking at the diagram, we have our first dipole, which we call our facilitating dipole, which is polar. And we have our second molecule here, which is nonpolar. As the polar and nonpolar molecules come close enough, they create what's called a van der Waals forces of attraction. The positive aspect of the polar molecule causes the electrons from the nonpolar molecule to come closer. Because opposites attract, we now end up with two polar molecules. Bigger the electron cloud, the stronger the dispersion forces, but they are still relatively weak. Intermolecular forces, as previously mentioned, deal or affect two other types of properties of the mixture. First is the viscosity, which is the resistance to flow. And you can see in here we have high viscosity to a low viscosity. The higher your viscosity, the higher your resistance to flow. So you're not going to flow as well. When you have a very low viscosity, you have a very low resistance to flow, so you're going to flow very well. When we look at surface tension, we know surface tension is the imbalance of forces at the surface of a liquid. You can think of things floating on water, such as this bug. This bug has high surface, the water has high surface tension, allowing the bug to scoot across. Surface tension is caused based off from the imbalance of forces at the surface of the liquid.